So first of all, again, thank you for the wonderful introduction. I like to start my talks off with what I call a picture of the day, and this is a photograph that was not taken by me, but a gentleman that I know named Wally Pachoka, and Wally is a phenomenal photographer of the night sky. And Drew mentioned that I have a fair amount of experience working at large telescopes, and the telescope that I worked at before I came to UO 6 years ago is the Gemini Observatory, which is this building right here, and that is the fourth largest telescope in the world, up on top of a peak called Mauna Kea out in Hawaii. And here in a minute I'll give you another little bit of info about that, but that's more to get me warmed up than you. But I also like to start off some talks with a story of our lecture, so you sort of know where we're going to go over the next hour or so. And I love to talk about a few of my favorite topics, including a cosmic perspective check. And again, this is how I hook my college students into the class on the first couple days, and we'll see if we can't sink a little intellectual hook into y'all. Also, my second favorite topic in the world is some interesting astronomy that's happened recently in the last year or two, that we sort of things that we see on the news, but maybe one layer underneath that a little bit, some more professional discoveries that have astronomers excited. And then my third favorite topic of the world, me, turns out. And so I'm three-quarters joking there, and so hold tight, and then I'm really excited about a Q&A. And I heard that there's rules involved here. Y'all are an unruly bunch with your questions, and so we're going to do Q&A after the first part of the talk. And so please, seatbelts on and tray tables up. We're going somewhere. I'm not sure where. The first point I'd like to make to all of us, and again, this is imagine you're a freshman just fell off the turnip truck, and we put you into your first big astronomy class at a big university like UO. You're sitting in a classroom with, 200 or 250 of your newfound friends, and you're scared to death because you're a liberal arts major in your first science class. And I try to get you on my side right at the beginning and say, look, I think that we all know that science is pretty cool. We just get it scared out of us. Typically that's middle school that does it, sometimes high school. And I like to say that I think that we are all astronomers, meaning every human being is an astronomer, at least a little bit. And the reason is that astronomy is deeply embedded in our lives. So deeply embedded that we don't even think about it much anymore. But it turns out that when are we active as animals? During the day. And when are we generally not so active? During night. Well, it turns out that that's astronomical, right? The sun is up during the day and the sun is down at night. How do we measure how long we've been on this beautiful blue marble? Well, it's how many orbits we've taken around the sun, and we celebrate that day that we were born, and we celebrate it a year later when the sun comes around, or the Earth goes around the sun again. And I think that all of us in this room can probably imagine a time that we were out under a dark sky or a sunset or a sunrise, and you look up and there's majesty up there that we're connected to in a fundamental way. And it's been an extremely rare student or person that I've met that has not had some sort of interesting connection to the sky. And I also kind of make a joke, again, remember now you're 19 and 18 and sitting in class for the first day, and I kind of make a joke and say, look, a little astronomy knowledge goes a long way. And so I tell the students that I consider that this class was a success if at the end of the class you find a significant other, a blanket, a dark sky, and some beverages of your choice. And you go out and you share the dark sky with somebody that you got a crush on. And I like to say that astronomy helps. Turns out as a smashing good-looking bald astronomer, I've done okay with the ladies in my life, and the astronomers and the astronomy helped quite a bit. And so I think it's more, again, can we open the students up to the idea that you can like science and other things. It's okay to like science and football, or science and writing, or science and French, or whatever you want. You don't have to be just a scientist. And that's where we go with the class. So let me kind of talk about me for a second. I'll get it out of the way and get it out of my system. But again, I show this is what I show to my students. And the first thing I say is I am you. Well, I was you some number of years ago, where N is now like 30. And because I was a state schoolboy. I got an AAOT from a community college called Lake Sumter Community College in Florida. And then I was an exchange student for a year. where I went and spent a year. Actually, now that this crowd, you all will remember West Germany. Turns out I spent a year in West Germany, a country that doesn't exist anymore. And then I came back and did my bachelor's degree and PhD at the University of Florida. So I'm a state school boy all the way. I had scholarships that are equivalent to what are some of the state scholarships that are here in Oregon, duck support and things like that. But I did an interesting thing. This is my first teaching job, and as a mid-career person, the first part of my career, I spent about 15 years or so working at some of the largest telescopes in the world. The Gemini Observatory is one of them, and I'm very proud to say that I brought that knowledge with me to UO, and that's one of the things that I think is a unique aspect of what we're doing down there in Eugene at the moment, is you have a person like me that is connecting Oregon students back to these big facilities, back to big telescopes in Hawaii and Chile and Spain, and lots of other stuff sort of mixed in there too. Again, for this crowd, you might be a little bit interested in that. Just right before I came to UO, I spent 3 years in Washington, D.C. working at a place called the National Science Foundation, and I was one of the folks who funded astronomy. And I had I gave out about $15 million a year in grants that funded astronomy programs. And boy, let me tell you, if you want to be popular, everybody wanted a piece of Dr. Fischer during that. Let me tell you, during those years. I was even more popular than I was in high school, if you can imagine. That was a very low hurdle to jump, but nonetheless, it won nonetheless. But what it did is that gave me a very interesting insight into how astronomy and how science is funded in the US. And that's allowed me to bring some of that insider knowledge here to UO, and I'll show you how we've leveraged that later on. I'm proud to say that I pick on the students where I tell them I'm from Florida and say, go Gators, go, and they all go, oh my gosh, 250 of them, and then I say, well, no, go Ducks, as a matter of fact. And I even tell you, I was so brave, I showed the same slide in Corvallis a few weeks ago. And, but it turns out that I have a very special relationship with the Duck, and I got to be a guest coach for the football team and got to follow the team for a day and watch a game from the field, not with the common people up in the stands, which it turns out those were the students. And so the point being is that I'm very proud and happy to be on the faculty at UO, and we're doing some great stuff down there. And I'll spend a few years, it'll feel like a few years before this is all over, but a short while telling you about all the stuff that we're doing down there. Okay, so enough about that guy. First thing we have to do is we have to have some common language. And again, maybe in this group, I'm preaching to the choir a little bit, but let me tell you about these liberal arts freshies that are coming in. They know nothing. As a matter of fact, I even like to say that they have negative knowledge. And that's hard. That's hard to do. But you know what the reason is almost every student in my class, well, they know what sign they are, and they probably read their horoscope, in the not too distant past, but they don't know what a planet is. And so we gotta dig them out of this kind of negative knowledge hole a teeny bit. And we spend the first couple of days of class really working on vocabulary. And it turns out planet is the first thing we want to talk about. And a couple pictures of planets. These are recent pictures. Everything that you're going to see here is within the last few years. But to be able to define these objects is something slightly different. And I want us to look at this definition a little bit, and I'm going to show you a definition of something different later on, and how there's going to be a big change. And the one thing to keep in mind is that these planets shine by reflected light. When you look up in the sky and you see Mars or Saturn or Jupiter, that's not somebody on Saturn that left the outdoor lights on, right? That's sunlight that went up and hit the planet and reflected off the planet and is coming back and hitting your eyeball. And we're going to talk about exoplanets here in a short while. And the fact that these planets are not luminous, they do not give off their own light, makes them extraordinarily difficult to discover, but we're doing it anyways. So keep this definition of planet in mind as we go forward. And I want to show the students and you all, this is part of this perspective check that I like to call the cosmic perspective check. And I love this picture of the planets. And there's let's just count them out. 1, 2, 3, 4, 5, 6, 7, 8, the 8 planets that we have in the solar system right now. It's only models. But the key is that these models are to scale. and that means the relative sizes of these planets, these models, are correct. And right there's Earth. Let's just go through them real quick. You got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And the relative sizes of those models are correct there. And I think that this is the beginning. And as I look out across here right now, I'm very happy to say that I see the same sort of expressions that I see during the class when I show this the first time. And folks are kind of like, yeah, Fischer, we sort of knew that. But at the same time, kind of like, oh, wow, that's Earth, huh? That's pretty, that's it. And so let me take this to the next level and show you this. And that is the sun on the same scale as the rest of those planets. And now, here we are. There's Earth right down there, that little fella. And let me point to the moon. Right there next to him. And this is what I call our first cosmic perspective check of the term. 109 planet Earths will fit across the diameter of the sun. And again, this is, I'm excited to talk to y'all because it's such a different thing. I can make a couple different references. Think of a beautiful string of pearls that are just draped across the front of the sun. 109 Earths will fit across the front of the sun. And already that's an absurd statement. Have you ever even thought of 109 planet Earths in your whole life? No! Why would we? There's one Earth. And I'm asking you all of a sudden to think of a chain of 109 of them put right next to each other. And that is what will fit across the front of the sun. And I think that this is, again, this first moment where people were like, ooh, wait a second. I'm going to learn some stuff here that I had not thought about before. And I try to bring it home to them. And it's scientific Photoshop. Whew. We're not that close. However, that is a real picture of the Earth and a real picture of the sun, again, to scale. And of course, on this scale, the sun would be a massive, huge thing. And then I think it brings it home. This is the final. Don't look at the sun, please. The nightmares that I have about their headlines in the Eugene paper. 2 UO students blinded. Dr. Fischer said, look at... No, Dr. Fischer did not say look at the sun. Don't look at the sun. However, the next time you're at sunset and you see the sun out there along the horizon, take a peek at it. And when you take a peek at it, you think about the fact that 109 of our planets can fit across the diameter of that thing, the front of it. And it takes a while for that to sink in. But I promise you, if you do that a few times, one time you sit down there and you actually have a moment and you go, geez. And when you really kind of internalize the idea of how big the sun is. And by the way, we love the sun. The sun is our star. But it's just a star. It's just like any of those other spots that you see on that picture right there. I like to believe that there's a bizarro ICL out at Willamette Prime University on the 4th planet from one of those stars. And right now, bizarro Dr. Fischer is right there right now giving a talk to a different crowd. And that crowd's looking up in the sky from their planet. And from their home planet, our sun looks just like that, like any other star up in the sky. Now, it's special to us because it's ours and it's so close, we can actually see the size of it. We can see that the sun, it's called the sun is resolved. We can see the angular size of the sun, and we now know that 109 of our planets will fit across that thing. But in the big scale of thing, our sun is no different than any other star up in the sky. As a matter of fact, it's kind of a C student. It's not too heavy, not too light, not too hot, not too cold, not too massive, not too tiny. It's really kind of an average sort of star. And I like this idea of making us think about what would our solar system look like from somewhere else. And you know what it would look like? Any one of those little gold points up on that picture right there. Again, it's not that our place is not unspecial, but it's special to us in an interesting way. It turns out that this is Autzen Stadium, and the joke in class is that it never rains in Autzen, and if you're a duck, you've heard that before. But I was trying to get across this point of how big is the sun. And I love Google Earth. I'm a big satellite guy, and and of course, if anybody's not seen Google Earth, please go to Google Earth, and the first thing you have to do is look at your house. So please go look at your house at Google Earth, it's awesome. And then look at Pine Mountain, sidewalk. So when I was surfing around Google Earth one night, and I thought, how big is Autzen Stadium? You can measure distances in Google Earth. And if you measure the diameter of Autzen Stadium, right here, right across the 50-yard line, that's 665 feet. Turns out I'm 6'4". Anybody want to guess what 109 times 6'4" is? Real close to 665 feet. You are to a football stadium as the Earth is to the sun. And I tell that to the students, and I say, the next time you go to Autzen and you're sitting there, you remember crazy old Dr. Fischer standing up in front of the class. You are the Earth, and that football stadium is the sun. And that's a neat thing. Again, another way that we try to use these sort of proportions in some sense to bring the scale home. And so they all look at me kind of quizzically, and I'm like, no, really, if you took 109 of me, well, first of all, if there was 109 of me, I would form an army and we would rule this planet. Okay, but other than that, benevolently, okay, but other than that, if you took 109 of me and put me tip to tail, I would fit right across Autzen just like the Earth would go across the front of the sun. And that's kind of I think that's a thing for them, and it helps bring it home quite a bit. We are I want the students to know sort of the scale of things, but we don't push too many kind of numbers on them right at first. But I do think it's pretty interesting. One thing is that the temperature of the sun, and this is sort of common stuff you might hear about later on after this talk, is about 6,000 degrees. It doesn't matter if it's Fahrenheit or Celsius, it's 6,000 degrees. So it's about 10 times hotter than your oven sort of thing. But you can't stand up there. There's no surface. It's a gas ball, and but I do think this is interesting. We really try to bring in the idea of distance, and you tell everybody 93 million miles, and they go, oh no, wow, 93 million miles, and you're like, yeah, how big is 93 million miles? And it's farther away than Seattle, right? But 93 million miles doesn't mean anything to us because so we have to scale things so we can comprehend them a little better. So we introduced this idea of light time. And then how far does light travel in a certain amount of time? And it turns out that from the sun to the Earth is about 8 light minutes. And so when we walk out here after this talk and we feel the beautiful sunlight on our faces today, that light left the sun 8 minutes prior. It took 8 minutes to go 93 million miles to get to us. And that's very impressive, it turns out, but it gets a lot worse than that. And so I urge you, don't look at the sun, please, but take a peek at the sun sometime and try to think about what this thing actually is. It's a star, just like all the other ones up in the sky. It's ours, and think about the size of it a tiny bit. And then I think that might help in this cosmic perspective a teeny bit. So I want to move on a little bit and bring back this idea of planets. We're going to step. I'm just going to tell you the secret that I don't tell the students. I'm going to step you outside of the solar system here. We're going to build this cosmic scale in the next half hour or so. And so this is I think actually it's my favorite planet. Earth is third, I'm sorry. Saturn is by far my favorite. And this is a view of Saturn that you can never ever get from Earth. This is a picture of Saturn that was taken by a spacecraft called Cassini. Cassini was out around Saturn for about 10 years. It ended its life back in 2016, but did some wonderful things for us, including took this beautiful image of the planet. And this is a true color image. If we could go to Saturn, this is very much what Saturn would look like to our eyes. And the reason, by the way, that I can confidently say that no human has ever seen this except for this picture is this is actually the North Pole of Saturn. And Cassini was orbiting Saturn in what was called a polar orbit. And so you can't see this picture very well from Earth. But you know what? Let me show you the best picture of Saturn that has ever been taken from Earth. This was taken by the Gemini Observatory up on top of Mauna Kea. And by the way, Saturn is not pink and purple, okay? This is an infrared image that we took with a very specialized camera, and we colored the picture the way we wanted to. We wanted to highlight the fact that Saturn, the planet, is made from different material than the rings. And the planet is primarily like the sun. It's hydrogen and helium and a bunch of other chemicals. And the ring is actually a crushed up little moon. And so that ring is dust particles and ice particles and carbon dioxide ice and water ice. And the little spot that you see, that is actually a moon of Saturn called Titan. So that's the largest moon of Saturn. And I would argue that this is the best photograph of Saturn that has ever been taken from Earth. We can arm wrestle about that and talk tech if you want to, but try to trust me for a second on that one. Because what I want to follow it up with is I'm about to show you the best picture of Earth that has ever been taken from Saturn. You're in that picture, turns out. You all want Earth in 2013? Okay, let me see it. Okay, there's folks of a certain age in here. Okay, yeah. Were you in the Western United States, Japan, Australia, or Northern South America in July of 2013? You are actually in this photograph. Because that's the face of the Earth that was pointing towards Cassini when it took the picture. By the way, that's us. Every human being that has ever lived and every human being that is alive right now is in that picture. By the way, we're all on that dot right there. And you'll notice there's no strings holding it up. And by the way, there's no turtles holding it all the way down either, for the philosophers in the room. And I find this to be a profound image. And I have had a tear in my eye in the past looking at it. This to me is one of these moments where you can truly step outside yourself and get a perspective. That's our spaceship that we ride on right now. And we're riding 30 kilometers a second around the sun right now. And I will even admit to you all, somewhat embarrassingly, but not really that much since I've told this story before, 12:36 p.m., July 19th, 2013, at least one person in this room went outside and looked at his watch, and at the exact time, looked up where Saturn was in the sky and went, and waved. So, okay, that was me, but it turns out it wasn't just me. All around the planet, people went out and waved at Saturn when this happened. And folks took selfies and sent them to NASA, and NASA then made this mosaic of about 1,600 people that went out and waved. And I am right, no, I'm just joking, I don't know where I am. But I want us to sort of ponder this a tiny bit, and here, let me make my first soft pitch to you. You are all invited to come to Pine Mountain this summer. We have it open to the public on Friday and Saturday nights, and if you let me know when you're coming, I'll do my best to be up there, and I will show you Saturn with your own eyes through our telescopes. And then you can sort of have the full circle of seeing the best picture of Saturn from Earth, and then let us show it to you with your own eyes. So there's a soft pitch that we'll come back to later on. So this idea of planets, it turns out that this is an image of Uranus. And I'm going to be a little provocative, and I have done some etymological studies on this. And by the way, yes, you can also say Uranus. And boy, do the students love that, let me tell you. And so there's a joke in here that I'm going to tell. It's a little provocative here in a couple slides, but what the hell, we're going for it. This was a recent image of the planet Uranus taken by a telescope called the Keck telescope. That's one of the largest telescopes up in the world. And this is an infrared image of the planet, but this is pretty impressive because what we can see is just like Saturn and Jupiter, the outer gas giants, or by the way, ice giants, called Uranus and Neptune, they also have bands. And by the way, they have storms, just like the Great Red Spot. And you know what? They also have rings, it turns out. Very hard to see with our eyes, but in the infrared we can see them. And there's kind of some neat fun facts that I learned about this planet as I was putting this talk together. It turns out it's about 4 times larger than Earth, so we could take 4 Earths and put them side by side across the disk, 13 rings. And really interesting, I think that, again, things we don't think about much, but Uranus's day is only 17 hours. It's 4 times bigger than our planet, but the day is only 17 hours. But the year is 84 years. So you think about one time to go around Earth on Uranus is 85 years, but every day is 17 hours. So there's all these kind of things more just to kind of tweak our brains a little bit. And then the fifth thing that I learned is just this year, the Gemini, the telescope that I worked at, discovered that the atmosphere of Uranus contains hydrogen sulfide, which turns out is the chemical that gives rotten eggs their smell. And boy, has that opened up an entire new wedge of jokes, as you can imagine. Not only does Uranus have rings, but now we know it smells like rotten eggs. And the middle school boys have rejoiced. So there's the joke, but here's the serious note a teeny bit. We are still learning about our own planets in the solar system. And I think that it's amazing to us in some sense. We sort of think, oh, you scientists, you know everything. we know nothing. We barely know anything, and everything we discover something, 3 or 4 more questions pop up. And so this idea, I just want you all to know that we're still learning about the planets right next door, much less these things that are going on the other side of the universe. I think that's kind of a neat fact about Uranus, and that's something new. So I'll tell you what, let me go through one more of these real quick. A scaled solar system. I hope I opened your mind a little bit to the idea of how big things are. But let's take the next step out past the sun. And so we're going to use what I like to call the grapefruit scale, and we've taken the sun and we've shrunk it down to the size of a large grapefruit. Very proud to say that a student made this for me. It's a softball she painted to look like the sun. And because for all term, I would hold my hand up and go, imagine a grapefruit. And then I would say things like, damn, I wish I had a grapefruit. And one day they didn't bring me an apple, they brought me a painted softball. Close enough. The modern version of that. And so here's the sun. So we've taken the sun and we've shrunken it down to the entire sun is on this. Now what you didn't realize, pop quiz. When's the last time you had one of them? You know? So this is how this works these days. By the way, even in a class with 240 students, I'll make them do things. I make them stand up, I put them into groups, I hand out pieces of paper and make them do things. It's chaos, it's total chaos. But you know what I cannot make them do? Put their hand up. That's scary. And I'm not even mad at them, because that is scary. So here's what we do what's called a chest vote. This is what we're going to show you right now. So I'm going to ask you all, you all can read. So the sun is now the size of a large grapefruit. How big is the Earth on this scale? And all you have to do is right next to your chest, hold up 1, 2, 3, or 4. I can see your vote, but nobody else can. And that's the key. So take a second, and I'll tell you what, we're going to be behind today. Talk to your partner next to you if you want to, you know. But let's do a vote. Let's do a chest vote real quick. What do you all think? 1, 2, 3, or 4? Okay, we got a good spread. I see some 1s, some 2s. Oh, look at the bad students back in the back. Oh, they're voting. They got 3s. So now you all don't get to see it, but I can see kind of the distribution in the class. I would say that we've got 1s or 2s, and y'all are doing good. It's 2. The tip of a ballpoint. The silver star. So you can't see it, but there's a little ballpoint right there. That's how big the Earth is. And by the way, of course, because 109 of these would kind of fit across. So keep that in mind. That 109, that comes up a lot. So by the way, take this young lady's pen back. So there's the ballpoint pen tip. So now you're warmed up. By the way, that was the easy one because I'd already given you the damn answer. How far away is the Earth from the sun? 93 million miles, this guy. Look at Joker in the back right there. You get a silver star anyway, sir. That was an excellent, excellent answer. But if we scale it down, now we've got Earth is the size of that pen tip. How far away is Earth? How about a chest vote? 1, 2, 3, 4. Oh, everybody's a little more nervy this time, huh? A little scared, okay. And, oh, okay. What about the bad students? Oh, they're going right back there. That one young lady's got her hand like this. Yeah, it doesn't count. So again, a big spread. I can see all 4 answers. and a lot of abstentions on this particular one. 50 feet. So yeah, so not too bad. So you think, there's that. 50 feet. Maybe a little farther. A pen tip. Man, will you hold your arm up back there in the back corner? Right there with the red, there you go. Hold it right there, that's 50 feet. So you think there's the sun, our planet is a pen tip over there in the corner of the room. How big are you on that scale? Follow-up question. Tiny, not as big as you may think. So you think you're good, do you? Same scale, sun, Earth is over in the corner. The solar system would probably be the size of the campus. In Eugene, the solar system is about the size of the Eugene campus. So probably, roughly the size of Willamette. How far away is Alpha Centauri, which is the nearest star to the sun? So this was good. Let's do one last outcome. We're going to be done with this after this one. This was just to show you the type of active learning we try to make our students do. 3s, 2s, 4s, 2s. Ooh, bifurcated. We got 2s and 4s, and a lot of abstentions. This is insane. It's 4. Right now, here's our sun, right here in the beautiful connector room. There is also a glowing grapefruit on top of the Washington Monument in Washington, D.C. And that's our neighbor. The Earth is right there in the corner of the room. Microphone? Oh, shit, sorry. The Earth is over here in the corner of the room, and our neighbor star is in Washington, D.C. That's the closest star. And that, to me, is what you got to contemplate a little bit. You get the initial kind of here, but think about that a little bit. And so, when you come to Pine Mountain, or you go out and you see a beautiful dark sky later on this spring or summer, and you look up and you see that, every star that you see with your eyes is at least twice as far as our neighbor. And many of the stars that you can see right there are 100 times farther away than our neighbor star. And I don't even know what is 100 times farther away than Washington, D.C., like the moon or something, And so this is the scale that we actually live in. And we're losing that. We're losing our grasp of the grandeur of this in some way, and I'm doing my best to fight against it. And I'm proud to say that most of the students will make them come out and look at a dark sky like this and see. But this is the last big step. By the way, you go out at night, I'll bet it's pretty dark here if you get just a few miles outside of the town, a few miles outside Salem. It's pretty dark. All of us in the room can see about 2,000 individual stars on a clear night. And those are our neighbors. Those are the ones that are around us. Those are the individual points of light that we can see up in the sky. And that's an impressive thing already, because we're seeing objects that are many, many, many times farther away than this one that's closest to us, Alpha Centauri. And this is a picture of the Milky Way. Excuse me. This is a picture of a galaxy that looks like the Milky Way. The Milky Way is so big, we cannot send a camera out to point back and see us. We can't get that far out. So this is a galaxy that looks like our Milky Way. It's a spiral galaxy. And let me show you a little, it's just one of my few little animations. Watch the screen there real quick. Boom. The nearest star to us is 4 light years away, and our galaxy is 100,000 light years across. And that's amazing in itself, but let me show you one. Look right here, watch this. Let me do this again, ready? Oh, here he comes. Right, that little guy. That's a graphic of the duck. And every star that you can see with your eyes is underneath that graphic. I'll do you one better. Every star that you can see with your eyes is in 1 pixel. But I couldn't make the duck small enough that we could see what it was if it was 1 pixel. You can't see any of that with your naked eyes. That's what we use telescopes for, radio telescopes, infrared telescopes, and that sort of thing. What we see is this tiny little bit of the galaxy that's right next to us. And I also like to tell the students that we live in the burbs. We live in the suburbs of the Milky Way. Here's downtown, here's Portland, there's downtown, here's Eastern Oregon, and here's where we live, kind of in Eugene or Salem in the valley sort of thing. You know, not too far out, not too far in. We're about halfway out. And I find that to be an interesting thing. So let me finish, do you two more things. I'll tell you about star systems and one more thing, and we'll take a break for Q&A. A star system, this is another one of these definitions, is the star and everything that's around it. And by the way, we live in the solar system because the name of the sun is actually Sol, S-O-L. Be a lot cooler if it was S-O-U-L, and we could live in the solar, all right, that's all right. But yeah, but look, we live in the system of Sol, and that's why it's called the solar system. And at the moment, you know, we have the sun and 1, 2, 3, 4, 5, 6, 7, 8 planets. I'm setting you up so good right now. 8 planets. Yeah, that's right, 8 planets. And let's talk about this situation here real quick. Oh, I heard the groan right now already. So, the Pluto situation. 13 years ago now this happened. This all went down. Anybody remember what happened in 2006? Listen to him. Pluto got kicked out. Pluto got voted out, voted off the island, demoted, thrown out, has to sit at the kids' table. Look at Pluto, sitting at the kids' table. All the other planets hate Pluto. Brutal situation. Let me try to change your mind on that. I will even admit to you, sheepishly, that I was at the vote. I was in the room where they held the cards up, and I could not vote because I was not authorized in this particular committee. But I would have voted to boot it. I would have held that little yellow card up. Boom, see you, Pluto. And I now get the dagger eyes right now. And it's not nearly as bad as the students, the college students now. Guess how old they were when this happened? Like 5? They were pissed. These were the students that wrote the hate mail to people like Neil deGrasse Tyson. And not me, which was great. So folks were really angry about this. And I wouldn't be surprised if there were some folks in here right now that are sending me dagger eyes right now this second. But let me try, look, there's lots of words on this. Don't try to read this stuff, I'll read it for you. I'm here to tell you that this was a PR problem. You know what astronomers are really good at? Astronomy. You know what we're really bad at? Public relations. This was a huge PR problem. Pluto was not demoted, it was promoted. Pluto is the first of an entirely new class of object. And these objects are called Kuiper belt objects. Because where Pluto lives is not out there in isolation by itself, but in a belt, just like the asteroid belt where there are thousands and thousands of asteroids. Out past Neptune, where Pluto lives, there's another belt called the Kuiper belt. And it turns out that since Pluto was discovered, by the way, in 1920, I should say 1920, that's a typo, we've discovered thousands of objects out here in the Kuiper belt. And so back in 2006, astronomers were faced with a real conundrum. What are we going to do with the several thousand objects we've discovered out there? Does anybody want to live in a solar system that has 7,482 planets? Can you imagine the mnemonic we would have to learn? My mom's something, 9 pizzas. And so we said, look, we got an idea. Let's develop a new class of object. And we'll call them, unfortunately, dwarf planets. And there's where it went off the rails. Because for some reason, there's this connotation with the word dwarf that is negative. And there was a very small but vocal group of folks in the room, which I was involved, that we were screaming and we're saying, don't call them dwarf planets. You know what I wanted to call them? Plutinos. Thank you. Plutoids. Not as cool, but maybe it could have worked. Can you imagine if we could have came out to the public and said, we have promoted Pluto, and it is now Plutino number 1. How cool would that be? But no, but we got PR issues. So they went with dwarf planets anyways, and that caused a massive issue. But I'm proud to tell you that Pluto is still out there, doing fine. was recently visited by a spacecraft called New Horizons, and we got beautiful pictures of Pluto. We learned a lot about it. And that's not where it stops. It turns out that what our solar system looks like right now is we have 8, 9, 10, 11, 12, 13 planets. Dwarf planets are planets just like gas planets and rocky planets and icy planets. It's just a word that we put in front to help describe these planets better. And interestingly, it turns out science is happening now. It's not just stuff that old white guys did 50 or 100 years ago in a book. It's going on right now. In October of last year, a telescope called the Subaru telescope, again up on Mauna Kea, discovered a new dwarf planet. And then let me see if this little animation works. Let me walk over here and point real quick. Right here. If you can see that object flashing back and forth, these are two pictures of the same part of the sky that were taken about 3 hours apart. And what did not move are all the stars, but what did move was that object. And by watching and measuring how that object moves with respect to the stars, we can calculate its orbit. And what we found was a brand new dwarf planet. And so I'll do you one better. Just not 6 months ago, the solar system got updated again. And so, by the way, this is a crazy planet which we nicknamed the Goblin for the time being. And I think it was because they discovered it on Halloween or close to Halloween. All of the solar system and our planets, we're all way buried down in here in the inner solar system. And here's where these dwarf planets, some of these dwarf planets and these Kuiper Belt objects live. And so I'm actually pretty proud to say that as of October 2018, we can update this again. 8, 9, 10, 11, 12, 13, 14 planets. Our solar system has 14 planets right now. So you shake your fist at anybody who says we only have 8 planets. And give them one of those. I oughta, 14 planets we have right now, and I'll do you one better. You keep watching. 2 or 3 years from now, there'll be 20. Because now we have the technology to be able to go out and search and find for these objects. Pluto is pretty big and is pretty close. And so we could find Pluto back in the 20s with a little telescope this big. We now have telescopes that have mirrors as big as this room. Honestly, bigger. And we can see so much more out there. This is what sparked the Pluto controversy. It wasn't because we wanted to boot Pluto. It was because we had to do something about it. Because all of a sudden we knew there was going to be a bunch more. So look.
Hi, I'm Helen, and
Hi, Helen.
I just have a comment.
Yes, ma'am.
I've been to Pine Mountain Observatory twice. It is mind-boggling. It is fabulous. I just so highly recommend it. I just have to say that.
Oh, well, thank you. Now, look, then that was unsolicited. I promise. I don't even know her. Thank you. When were you there? Oh, good. That was since I've taken over. Oh, I'm glad. Okay, good. I'm glad that it was good. Thank you, though, ma'am. Nope.
Hi.
Yes, sir.
I'm Ken. Hey, the newer planets that you talked about, beyond 8, which are out of the ecliptic, out of the plane, are those thought to be captured objects rather than something that formed when the other planets formed?
This is a great question. What Ken is suggesting is that if you look at this graph, all of our planets are more or less in a plane. And by the way, we call that plane the ecliptic, is what it's called. And some of these are out of the plane a little bit. If our solar system is like this, some of these are tilted. But you know what? We do not think they're captured. We actually believe that all of the objects that we are calling dwarf planets are members of the Kuiper Belt. And the Kuiper Belt is the remnants of the disk that we formed from. And it turns out that when a star like the sun forms and is very young, it's pushing off tons and tons of energy. So much that it literally can push material away from it and evacuate an area around it. And all of the stuff that got pushed out of the inner solar system ended up in the Kuiper Belt. And so we do think that these objects, the dwarf planets, were part of us. They weren't captured. They've always been part of us. And by the way, quick sort of underneath note, one of the reasons why these objects are so interesting to study is that these are the material that our planet formed out of 4.5 billion years ago, but they're basically pristine. These are the objects that have not had weathering and continental drift and this type of stuff happen, or plate tectonics. So we can look at these objects and get a glimpse of the building blocks of the Earth in some way. But they were not captured. They're here. They're ours. Yeah.
My question is concerning what else is out there. Do you think there is anyone out there besides us? And what do you think of the mathematical observations or conjectures that have been put out by Shoemaker and others that, gee, there must be somebody there because here's the math for it, and there's so many of them. So do we have any way? We have no way of knowing, of course, because there's been no contact. But what's your guess?
Happy to help. This is something that I've actually put a fair amount of thought into, because you might not be surprised, it's not the first time I've been asked this. And so let me give you my nutshell answer, and then a slightly longer one. I am of the personal opinion that life is everywhere. I cannot shake this feeling. However, I think it's simple life. I think that there are planets that are covered in grass and trees, and I think there's planets that have viruses and amoebas and krill and plankton and things like that. And heck, we might even have dinosaur planets out there, because, by the way, our planet was a dinosaur planet. For 100 million years, the dinosaurs ruled our planet. However, I think that the difficult jump is to what we would call intelligent life, and meaning a species that can ponder what's up there. Yeah, I love my cat. I love my mom's cat. I don't think my cat cares about Jupiter. Not in a bad way. And my cat clearly is alive and has desires, and sometimes she hates me and sometimes she loves me. But to me, I think the hard jump is this jump to what would be maybe called sentience. But I am fairly convinced that there's life everywhere. And I'll even be so bold as to make a provocative statement. I find that it is my opinion that the best place that we can look for life right now is on a moon of Saturn named Enceladus. And Enceladus is a small moon. It's about the size of the Gulf of Mexico, and it's covered in glaciers. So we know there's tons of water ice there. And I'll do you one better. This Cassini, the spacecraft, discovered active geysers on Enceladus. And guess what's coming out of those geysers? Liquid water. And by the way, it's not frozen water, it's liquid. And subsequently, Cassini proved that underneath the ice, there's an ocean. And even more so, the very last thing Cassini did before it died was NASA did something that I consider crazy. They took a spacecraft and they flew it right through the geysers. And what the spacecraft detected is tiny little particles of silicon inside those plumes. It's crushed up sand, basically. And the type of sand that they found can be found here on Earth next to hydrothermal vents on the bottom of the ocean. And what surrounds hydrothermal vents on the bottom of the ocean? Ecosystems. And there is a ton of evidence that's pointing that underneath the ice in Enceladus, there are hydrothermal vents on the bottom of this ocean. And I'll bet you all $1. I'll bet each one of you individually $1. It's like $100 that we're going to find life on Enceladus. But I think it's simple life. So long answer, but it's a complex question. Now, why haven't we seen aliens? That's slightly tougher. If you've ever heard of things called the Fermi paradox or the Drake equation, these are some of the kind of mathematical constructs that we use to estimate. And I think ultimately the problem is that you all, look, this is the sun, the Earth is 50 feet away, the nearest star is in Washington, D.C. The scale. I cannot right now comprehend a way that any species can overcome the distance. And so that's why I think, but maybe they're out there, but they've never been here. Again, Long answer, but great question.
Yeah, could you briefly explain how you measure the size of the planets?
Oh, for sure, absolutely. So there's many different ways. It turns out that we know the size of all the planets in the solar system very accurately in two ways. The first way is we measure their orbits. When we look out and we see these things moving around the sun, we can map their orbits. And then through some very straightforward mathematics, which by the way this gentleman named Kepler came up with back in the 1600s, we can then, basically the mass of the planet is proportional to how fast it orbits around the star, and we can use some Newton and some Kepler to then get the size out. And so for all the planets in the solar system, we have very, very, very accurate measurements of the size, the mass, and because of that, we know their density very well. And that's how we can tell, for example, if it's a gas giant or a rocky planet like our own. Does that help a little bit? Yeah. Now, to be clever, it turns out that there are planets around other stars called exoplanets. And the way we measure the size of those planets is some of those planets orbit and they go right in front of their stars. And when they do, they cause the star to dim a tiny bit because they're blocking the starlight. And by measuring how much the star dims, how long it lasts, we can also determine characteristics of these planets called exoplanets. So turns out we're clever monkeys, us, and we can take data and interpret it in really interesting ways.
Hello.
Yes, sir.
Back to that, Encephalus, I think, was the name of the...
Enceladus.
Enceladus.
Yes,
okay,
sir.
Enceladus, sir. If we had a chance in a few decades to visit and sample that organic compound that may be replicating, would you dare bring it back here?
Now, there's a question I haven't been asked before. Well, let me just say this, is that already the evidence is strong enough that there is a spacecraft that is now being designed, and it's called ELF. And ELF is the Enceladus Life Finder, and it turns out it's actually one of those acronyms that kind of works. And so ELF is a spacecraft that's being designed to go to Enceladus, but not land. And this is a spacecraft that would have all the high-resolution cameras, but very interestingly, something called ground-penetrating radar. And this would allow the spacecraft to map underneath the glaciers. So there's that, we can map the ocean, and it would also have instruments on it that would actually be made to fly through plumes, for example, as opposed to Cassini, which wasn't. And so the idea would be, as a matter of fact, the one design I saw literally had a little scoop, and it flew through the plumes and scooped up some of the stuff, and that stuff gets funneled down into the spacecraft where you then analyze it, including with a high-power microscope, which we would look for single-celled organisms, amoebas, and things like that. So would we bring it back here? Not at first. No, we would leave it there. And I'll do you one more, is the reason that ELF is not designed to land on Enceladus is that we do not want to contaminate the surface of Enceladus with any human bugs. I mean, it would be a bummer if we landed something there and then we're like, oh, guess what we found? Staph! Oh, that sucks. A, staph is there, and B, oh, did we bring it? You know, so at first we are being very, very cautious about that, and the first spacecraft won't even land. They'll just orbit. So we're being very careful about that. Anybody who's read the book The Andromeda Strain knows why we don't want to bring them back here. Yeah. Yes, sir.
This is Harvey.
Hi, Harvey.
Could you discuss Planet X, please?
Oh, I can a little bit. So Planet X, that's something that's in the news right now. And the idea about Planet X is that there might actually be the 10th planet. And I would argue, well, heck, we already got 14, so it's probably the 15th planet. But what Planet X is when we look at the orbits of the major planets, including Neptune and Uranus, it looks like they have something tugging on them. And we can tell because what we were saying earlier is we can very, very accurately map the orbits of these planets down to a hair width. I'm not going to pull a hair, I don't got many left. But And so what it seems like, the data says, is that these planets there's something outside of the planets that are tugging on them, which makes their orbits a little bit wonky. And currently, we're trying to hunt down this planet X by using the biggest telescopes in the world, including that telescope called Subaru, by the way, is doing a big survey where they're going and taking this large telescope and taking very, very deep images of parts of the sky where planet X might be. And so this is a question that's going to be answered in the next year or two when we map this part of the sky where we think this thing is, and it's either going to be there or not. But that's what it is. If it is, it's a planet it's an object that's bigger than Pluto, that's hiding out there in the Kuiper Belt somewhere, which we haven't detected yet. And so I think it's an open question. Planet X might actually exist out there.
Now, did you want to continue with your slide presentation and then come back to more questions?
Yeah, sure. I'll tell you what. If you are okay, let me have another 15 or 20 minutes, and I'll tell you about Pine Mountain. And let me make a pitch for you and show you some educational stuff that we're doing. How's that sound? We good? All right, let's do this. That's next time. You got to come back. We'll talk about that. So again, we don't need another picture of the day, but I thought this might be just a fun one just to show you real quick. This is a photograph I took, 10 years or so ago now. And that's I was standing on top of this mountain, Mauna Kea, out in Hawaii. And that's the shadow of the mountain, is that triangular, very broad shape. That's the shadow of the mountain. I would be standing, right here, up at the tippy top. And that is the moon rising, just rising in the east, and it just happened that the moon was in a lunar eclipse. And so there was this 1 in a sort of gajillion chance that you had the moon inside the shadow of the earth, inside the shadow of the mountain. And so I couldn't stand it. We had to take a picture. And so again, just kind of a pretty, what I kind of tell the students, maybe y'all are looking for a third career, that you try this astronomy stuff out. It turns out you get to go, and this is the view from your office every once in a while. So it's not such a bad thing. But let me talk about something a little bit closer to home, and something that's very dear to my heart. This is Pine Mountain Observatory. And our colleague here will keep me straight, make sure I'm saying everything right. And here's a picture of our observatory, and this is over in Central Oregon. This is about 30 miles east of Bend. I mean, heck, I rode by State Road 20 on the way up. You go to State Road 20, turn left or right, and just go. And then 4 hours later, turn right again, and boom, you're at Pine Mountain. And up at the top of the hill, we've got four telescopes, and there's a nice little family portrait that was taken last summer for us. Let me tell you a little bit about Pine Mountain. That's Pine Mountain during the day, and then the fireworks come out at night. There's Pine Mountain during the night. This is a photograph taken by the way, a UO student, a little sophomore, barely 20 years old, this guy, Justin. And boy, it turns out Justin is awful handy with the camera. And Justin has taken some beautiful PR images for us of the observatory, but this is very much what the night sky looks like up there. And it turns out, again, that all of us in this room of a certain age, it takes our eyes a little longer to dark adjust. The students, you walk up there with them, and they're like 5 minutes later, like, oh, can you see that? And you're like, no, not yet. Shut up. 20 minutes later, I'm like, oh, yeah, I can see it. So I invite us all to come up, find a bench, sit down for half an hour, let our eyes dark adapt, and you get to look up at the sky and see something like this. Let me give you just a little, the problem for me with Pine Mountain is I love our fine rectangular state of Oregon, and here we are right now, Salem. Here's Willamette Hall. There's where the physics department is down at UO, and here's Pine Mountain. Turns out that's 171 miles. From the UO campus to where the telescopes are. And so that's a bit of an issue, it turns out. And here's one thing that I do not want to do, and that is take 10 busloads of UO students to Pine Mountain. That sounds like a very bad headline. 5 students wander off in the woods. No, let's not do that. So I'm going to tell you about a clever way we're going to fix that. Again, this is a picture from Google Earth. And if you zoom in down onto the observatory a little bit, what you can see is we have a complex of buildings. There's 1 telescope, 2, 3, 4 telescopes, a little 5-room dormitory, an operations center, a little welcome center, and a circus tent. And the circus tent is where we used to give little public talks and things like that. The tent, unfortunately, is gone. But we still give public talks and things up there. So the point is that it's a small little observatory, and the beauty of it is it's ours. It's mine, yes. Well, it's UO's, but they let me run it for them. And it's a 9-acre campus of UO campus in the Deschutes National Forest. It's about 6,500 feet, about 25 miles east of Bend. And I like to say that the first telescope was built in 1968, a vintage year, since that's the year I was built. And then the last telescope was built in 2015. So there's a bit of a span of range in there. But my students and I have built the 4th telescope up there. And let me tell you about that little telescope a teeny bit. Here's my first and really the only pitch to you. Is that we are open to the public on Friday and Saturday nights, and it's a heartfelt invite. Anybody who comes and listens to me prattle on gets to come up to Pine Mountain and listen to me prattle on more. But there I also have props and telescopes to show you the sky. So get on up there and come up and visit us for a tour. Let's show you some pictures and not all these words. I did not show you much about me beforehand, but I want you to take a look at the picture on the left side of the screen, and that's a former colleague of mine who is a full-size human being, as a matter of fact, standing inside the Gemini Observatory. So there's Taylor, and there's the telescope. By the way, the telescope is 75 feet tall, just to give you, it would barely fit in this room. And here is Taylor standing in Pine Mountain. And so it's a slightly different scale of things, but on the other hand, the beauty of Pine Mountain, like I said, it's ours, and we can do whatever we want with it. And but one thing that we try to do is we are running Pine Mountain is what we like to call mini Mauna Kea. It started off as a joke, and it's turned quite serious. And the reason is that we are running our little observatory just like the professional observatories of the world. And to me, that is an excellent training facility for the students. It is, we make them do things like they have to check in, they check out, there's procedures, they have to write updates, they have homework, they have exams, they have a job when they come up to Pine Mountain. And it's prepared them quite well, and I'm very proud to say that I've had 8 students in my research group in the 6 years I've been at UO. 6 of them are now in graduate school in astronomy. And so this is working. And by the way, 4 of them are young ladies, and I'm very, very proud of that. And so what we're doing is we're building a pipeline here in Oregon where our Oregon students can come through Pine Mountain and then go and work at the biggest facilities in the world. And then we're real proud of that. That's something that we're working hard to do. The machine that's let us do this is called the Robbins, and this is a little 14-inch telescope that, again, we've built from scratch. Let me be careful. We've bought the components of the machine that we then put the machine together from scratch. We didn't build the telescope. We sort of bought the telescope, but we recently upgraded the telescope, and we lovingly called this one the Blue Bomber. And this was a 1994 Ford Focus. Is what this was, and this is a 2019 Cadillac. And so we had a big upgrade last summer, and we now have up at Pine Mountain I would argue this is one of the highest tech small telescopes that in the US right now. This is all very top line scientific grade components, and we just started using it for undergrad research last year. And by the way, if you all come up, I'll set you in the control room and you can take a picture with this telescope. Don't tell the students. So we don't care about that stuff so much. That's a bunch of techie stuff. But here's some dude. Got him right there, shiny bald head, sitting in the control room. There's our little control room for the Robins. And again, here's the invite. Come up and we'll sit you in that big chair, and I'll sit next to you and show you where to click, and we'll take a picture with the telescope with you. So the idea point is that for the public, it's more of a outreach tool. We want to let you sit in the big chair and show you some science. But it turns out that when we have the public night, you all leave at like 11 o'clock. You're like, oh, it's time. Oh, I'm getting tired. And you all go home. And then the fun starts. Because we get rid of you, and then we bust the telescopes out. and then I usually last until 1 or 2, and then I turn it over to the students, and who the hell knows what time they go to bed. And so that's when they're doing our actual research projects up there. Let me tell you a little bit about one of them. We'll skip that stuff for the moment. So the students in my class are everybody but the science majors. I had 225 students in winter term, and I had 0 science majors in my class. And I'm not even mad. My class is made for everybody else. Journalism school, artist, the entire women's basketball team, Go Ducks, made the Final Four. So everybody but the science majors is in my class. And so I tell them stuff like this, and here's your last pop quiz. Back at that big telescope that I worked at in Hawaii, I literally called a couple months ago and asked this, and I said, how many people are on the staff? 110 people are on the payroll of Gemini. How many of those folks were PhD astronomers like me? And again, I'm not even going to pick on you. And the students, I break them up into groups, and I make them list different jobs that can be at the telescope and how many astronomers and this sort of thing. Actually, it's 10%. There are only 10 astronomers that work at the 4th largest telescope in the world, and 100 people that do everything else. Mechanical engineering, software engineering, purchasing, receptionist, person who keeps the fleet of cars running, the person that writes the visas so we can go to Chile, the admin folks, HR. These facilities are for everybody. And I don't think the students that are coming through my class recognize that. So it's important to make them realize that if you're a journalism student that loves science, be a science journalist. Turns out that's a thing, and you can go and have a job and a career afterwards. And so we tell them little things about like that. I got like 10 minutes and I'll stop. So there's that guy's bald head again. And so this is the what we call the common room in the dorm up at Pine Mountain. And I happen to know, I remember the moment this was about 5 o'clock in the morning one morning. It was freezing cold up there. And so quick sidebar, which one of those students is from California and which one is from Oregon? Jacob is from Oregon. Lindsay is from California. So anyways, we were freezing our toes off, but none of us could sleep because this was the night after we got our very first research grade data. And it was just like, woo, we're all abuzz, and we had to come down and work on the data. And what were we working on? Well, this right here. This is, again, this is 3 summers ago now, June 2016, and that's a picture of a galaxy named M66 that those students took with our telescope. And by the way, it wasn't me. They do it all. I just tell them what to do, and then they go and do it. It's uncanny. And so this is a pretty interesting image. Let me show you a different picture of it. This is 3 different pictures that we took that we could then stack and make a color picture. So this is roughly what that galaxy would look like if you could see it with your eyes. And every spot, every little point of light that you see on that picture is a star in the Milky Way. Those are the few little sprinkling of stars that just happen to be between us and this galaxy, which is much, much, much farther back behind those stars. Everyone except one, that is. That little fella right there is a supernova that exploded in that galaxy 55 million years ago. It was a Thursday. I'm joking, we don't know, okay? 55 million years ago, that supernova exploded in that galaxy, and all that time, that light has been traveling towards us. And in June 2016, it passed Earth, and we were at Pine Mountain observing when it did. And so we caught the supernova. It turns out we were the second group. It was observed, detected in Australia. And the moment it got dark the next night, we were already sitting on M66, and we got the second images of it. And I was like, that's pretty damn cool, man. Little Pine Mountain in Oregon, we got the second pictures. And so what did we then, with the students, we then did what we analyzed the data. We determined how bright that object is. It's just some number. Don't worry about what the number means. But that little spot of light is about 10,000 times fainter than what we can detect with our eyes. And by the way, this is a little telescope that's only, about the size of this podium. And already the modern technology lets us do incredible things with it. So this was a beautiful sort of sense or proof of concept for us. And we now have 4 different projects going on up there. And I want to mention one of them, just such a neat connection to the building that we're in, is we have a very strong collaboration with Kobe University in Japan and a place called Sanda Technical High School. And last summer, we had our first group of Japanese exchange students come and spent a week in Eugene and a week up at Pine Mountain. And during the week there, we taught them how to use the telescope. These are sciencey students, and observe. And we have an ongoing research project with them. And for the next 5 years, we're going to have UO students go over and Japanese students come back here and forth. So a wonderful connection that we have there. But we have to solve this problem. Here's the last topic, I promise. I still have this issue. 170 miles between campus and Pine Mountain. So here's what we're going to do. We're going to build the rock. And I did not come up with that. We had a contest, and the students came up with the acronym. The University of Oregon Remote Observatory Control Center. That little telescope that we built is a robot. And we designed it from the ground up to be robotic. And what that means is that as soon as we get the internet connection upgraded to Pine Mountain, which is going to happen hopefully here this spring and summer, we are going to be able to observe from Eugene. And I'll do you one better. I got a room allocated to me on campus down in Eugene in Willamette Hall in the physics department, and we're going to build one of these. A remote control room where the students can literally sit there in Eugene and use the telescopes at Pine Mountain. And if we do it right, it's going to look just like the bridge of the Starship Enterprise, with 7, you'll notice there's 6 clocks, and what you cannot see is a big leather chair sitting in the back where I get to sit and say things like, make it so. And engage. And anybody who's a Jean-Luc Picard fan knows exactly what I'm talking about. And so this is coming, folks. We think that in the next 6 months or so, we're going to have the room and the internet upgraded. And as early as next fall, when the students come back, we'll be able to observe with Pine Mountain from here. And I'll do you one better. A year from now, invite me to come back, and we'll do an evening session, and we'll observe with Pine Mountain from this room. Done? Done, we'll do it. And we'll come in and we'll log on, and I'll sit up here, and heck, I'll bring 2 students and make them work. And we'll sit up here and we'll do it. And so look, that's it. Basically what we want to do is my goal is to open Pine Mountain back up and make it a resource for the students, but also at some level for all of us. And that's a heartfelt invite. You come on up, and we'll put you to work running the Welcome Center and greeting the folks, or I'll do you one better. We'll team you up with a student, and you can push a telescope around, showing the public Jupiter and Saturn or a star cluster. And that's it. I'm tired of talking, and you're tired of listening. Thank you, and let's hang out a little bit and do Q&A again here at the end. Thank you all.
This is Ken. I was sitting right by the mic guy here.
You're first.
I was just curious if you could describe a little bit the technology that surrounds that telescope that makes it do such phenomenal things.
For sure. As a matter of fact, let me go back to this one techie slide, folks. And it turns out that the students wrote this, so I know just an ooch more than you do. It turns out that modern telescopes, they have 3 pieces. There's the telescope, which is the optics, and for us, that's this monster carbon fiber beast, which that's a top of the line caddy right there. Power windows and AC, baby, all the way down. And then the second component is the camera system. And actually this whole thing is the camera. There's and these is a digital camera. I'm sorry, I wanted to show you just like the camera that's in our cell phone. But this one is a super duper science version, and that is the Maserati camera of Italian beauty, and what makes it special is the chip, the detector that's inside the camera. That camera is made for one thing, and that is to see things that are faint. we could not use that. If we took a picture in this room, that camera's dead in this room. It's way too bright for us to use the camera in this room, even with a filter. And then the third part, which folks don't think about, is this white part. That's what we call the mount. And that's literally the thing that's bolted to the cement pier, which is bolted to bedrock. So that's the thing that the telescope sits on, and that's actually the brains of the operation. There's a little computer, not in the telescope is just a lens. Let me be careful, it's a very special lens, but it's just a lens nonetheless. It's the mount that's where the smarts are. And what we did is we made the conscious decision to say, look, we would prefer to have a slightly smaller machine of very high quality, as opposed to a bigger machine that we had to futz with all the time. And so this was, and this is a ton of money, right? That machine is about a $100,000 machine. So that's not nothing. Gemini was $120 million. So I'm small potatoes compared to the big science. But I think that the bang for the buck we're getting is strong here. We have the student development, we got the public engagement, and then this idea of technology development too. So the point being is that most of this stuff is off the shelf. You can go and buy these components, but we were very clever and used my insider telescope knowledge to put together what we think is a very strong system. So that's kind of the tech side of it.
Okay. I think most of us have probably seen the recent story about the photograph of the black hole.
Yes, sir.
What is this, do you regard as the significance of this?
Yeah, that's a great question and very relevant. I mean, gosh, what a huge thing that was, and it looked like a black hole. It was a black hole in the middle of the picture. So those of us in the know, we sort of had a feeling for what it was going to look like. We sort of knew the capabilities of the technology, but the significance of it I find is twofold. First of all, it is hard data. That is an actual photograph of these objects that we have mathematically shown to exist. You can't, it's right there. We can see it. And interestingly, the folks who are analyzing that data have already said it is they can measure the size of it and these are meeting the predictions that the models made. And so that gives us a very strong reinforcement of the models that we use to talk about these things. But for me, I am a tech telescope guy, and the technology that went into making the image is just as mind-blown as you all were when I told you the nearest star is in Washington, D.C. That's how much my mind is blown, the fact that they made this work. This is an array of telescopes that folks, they all observed this target, and then they literally took the hard drives and put them on airplanes, and they all flew the airplanes to this one site in the world where we probably saw the picture of the young lady who's sitting like this. She took all of that data and combined the data together to make the image. And the fact that the technology that's gone into it is opened up a whole new era of astronomy for us. And so we sort of knew what we were going to see, but the fact that it looked like what we predicted is an incredible strengthening of our understanding of those objects. That was a long answer, sorry, but a good one, hopefully.
This is B.
Hi, yes, ma'am.
Would you discuss binary stars?
Oh, I sure will. Binary stars. So those are sort of maybe exactly what you might think. So here, I'm going to give you a homework assignment you didn't even know. The next time you go out and you look up at one of those beautiful dark skies where you can see a myriad of stars up there, 7 out of every 10 of those stars have a double, which means those are 2 stars that orbit each other. And they're paired together, and they were born together, and most of them will live their whole lives together. The sun is actually a little bit of an anomaly. The sun is in that 30% of stars where it's only a single star. And so it turns out that we have recently discovered planets, exoplanets, that have binary stars, and the planet orbits both of those stars. So if anybody remembers the old Star Wars Aldebaran, where Luke lived and the sun had the 2 stars sunsetting, that is actually real. There are planets out there that have 2 stars in the sky. Does that help a little bit? What they are, but those are literally 2 stars that are formed together and orbit each other for their entire lives. And there are also triple stars that have 3 that do that every once in a while too. Yeah, I bet you do. But interestingly, what you also can get is configurations where it never gets dark. Weird to think, right? Or the stars are separated so far in the sky that you never get full darkness. You only ever see twilight and stuff like that. Yeah, so it's weird to contemplate actually.
Hi, Ken here.
Yes, sir.
Exoplanets are discovered by 2 different methods, optical eclipse or moving the star.
Yes, sir.
And that would mean that they have to be more or less in the same plane with us.
That's right.
So would you discuss a minute what about all the others that aren't in the same plane? And before I
Sure
let
can.
go of the microscope, I'm going to take up your bet. $1 right here. I hope you win.
The gentleman puts his money where his mouth is. I like it. So look, well, hold your eyes real quick, and let me show you something real fast. Doot, 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 doot. Boop, that one right there. So as Ken said, an exoplanet is a planet that orbits a star that is not the sun. And now I got to rant for a second. As a matter of fact, let me show you something real quick. I skipped this part, and I'll come back and talk about this next time. But I want to show you this slide right here. I will arm wrestle anybody in this room about this, except that guy in the back. He looks pretty big. I will argue that 1,000 years from now, there's going to be a little entry in the Galactic Encyclopedia, and that entry is going to be called the 2000s. Just like if we went into the encyclopedia right now, there's a little entry called the 1000s. And I will argue that it's going to be a paragraph long, and one of the things that we are going to be remembered for is we are the generations that discovered the exoplanets. 1,000 years from now is when people are going to be going to these planets, and we are the ones who gave them the targets. So these are planets that are around other stars, and we discover them in 2 ways. Sorry, I'm going to go back to this picture. And both of them need a very particular configuration. They need that planet orbits so that it goes in front of its parent star. And if you look, every colored spot on that picture is where we've discovered a planet inside this part of the sky. And they've all been discovered through what's called transit. The planet goes in front of the star. As of today, 3,999 of these planets have been discovered. It's an incredible thing. And we now know of so many of these, we can start to do statistical analysis. And we know that we have discovered so many that are in this perfect configuration, we can now estimate how many are in the non-optimal configuration. And it turns out that, it's right here. Just sort of last year, the folks who study this have come out with the current idea that on average, every star in the sky has 1 planet around it. And that is a profound statement. Look, I might be the youngest person in here, maybe not quite. In 1990, there were no planets known outside. Every one of you in school, none of you learned that there were planets outside the solar system because we only discovered the first one in 95. The damn students in my class were born that year. And since then, we have confirmed that there are 4,000 out there. And when you all go out tonight, it might be clear tonight, and you look up there in the sky, every one of those points of light has a planet around them, on average. Some of them have none, some of them have 14, us. But on average, there's about 1 out of every. Does that help a little bit? This is a big deal. I think this is the discovery that we will be remembered for in the deep, deep future. That and probably just the invention of the transistor, maybe, because it caused computers. Yeah.
Hi.
Yes, sir.
This is Roger. I have a question concerning your telescopes. They're very sensitive instruments, and I imagine that temperature variations must be a big problem. How do you
Absolutely.
compensate for variation in temperatures?
Sure can. Boy, you're speaking my language. Again, hold your eyes real quick so I can go back here and show you this monster. With the idea of being smaller but more powerful, what this particular telescope has is there's two mirrors. If we were observing something right now, the light would come in the telescope, hit a big curved mirror, bounce up here, hit a second mirror, go back through a hole in here and hit the camera. It's called a Cassegrain telescope. And both of those mirrors are actually heated. They have electrical wires embedded in the glass, and we run a small current through there, and we keep the mirrors about 2 degrees Fahrenheit above the ambient temperature. And so one, it takes care of thermal expansion and contraction, but you know what else it takes care of? Dew. What are things astronomers hate? The daytime, turns out. Clouds, turbulence, and dew. Ugh. So the point being, we actually heat the mirrors. That's a great question, though. But we heat the mirrors to keep them, A, dry, and B, to deal with the thermal expansion. What about the rest of the structure? It turns out that this particular telescope is 100% carbon fiber, and because of that, the expansion is minimal, and it's compensated for by the motors on the mirrors. But that's fun tech right there.
Okay.
Yes, sir.
This is Wayne. I have a question. While you're remotely operating this at Pine Mountain, do you have backup at Pine Mountain for critters crawling in or things
we
not
do.
working?
So I actually can tell that where the practical folks are. And here's one of them. So we love our telescopes, our little mighty telescopes so much, is I am way too paranoid to let it be operated completely remotely. So I have one staff person that works up at Pine Mountain, and when we have done the remote observing tests, he's standing right there. And by the way, he's 10 times worse than I am. He will literally stand there with the the phone and like, okay, hit the button, all right, okay, it's moving. We baby that baby quite a bit. But the idea is once we get the procedures in place, and by the way, we have 4 cameras, one inside the dome, one pointing down, an infrared camera so we can see at night. So we can see what's going on, but we're not ready to cut the cord yet. And so we won't have true remote observing for another year or so. But I promise you, when I come back here, we'll make Alton be at Pine Mountain so we can open it up and use it.
Yes, this is Lynn. Hubble has gotten enough information out to those of us who are not astronomers, and I'm sure that Hubble is powered by solar energy that keeps it going 24 hours a day. How much possibility does U of O and your group have at using Hubble and helping your own information with your other scopes?
Yeah, maybe not as much as you might think, but not in a bad way. That is, when I worked back at Gemini, that are the type of telescopes that collaborate with Hubble, right? The top flight, sort of ones. What we can do is complement what they do. What Hubble and the big telescopes, they are hindered by one problem, and that is time, just like you said. For every 1 hour of Hubble time that's used, there are 50 hours that can't get done. But we have the opposite problem. We have all the time in the world, we need projects. And so the type of projects that we do at Pine Mountain are those projects where we can take a chance and try to detect a supernova. By the way, 99 times out of 100, we don't, But the students that are running the telescope get to take the data. So for us, we are about 75% educational and 25% research, where the Hubble is 100% research. And so I would say that we can complement what they do but unless I wrote research proposals that went against all of the other research proposals, we don't have any direct access. But we're not mad at that. We're trying to do something a little different here. We want to train up the undergraduates so they can then go to graduate school and become graduate students that are qualified to use Hubble. And so we're prepping them. We're going to prep them up and get them ready to use the big ones like Hubble and Gemini, but no direct access. Yes, sir.
What are the theories behind the existence of galaxies that are made of almost entirely dark matter, and galaxies that are devoid of dark matter?
Yeah.
Greyhawk 44?
Yeah, right. So what the gentleman is asking about is even recently there was a galaxy like the Milky Way, these are incredibly large objects, and embedded within those galaxies are something called dark matter. And we have observational evidence that this stuff exists, but we can't detect it. It's annoying that we have no way of detecting it. And what we have recently discovered is that the vast majority of galaxies have luminous matter, by the way, what's called baryonic matter. That's the stuff we're made of. You poke yourself, we're made of baryons. That's about 5% of the universe. 25% is this stuff called dark matter. And we have recently discovered galaxies that seems like they do not have any of this dark matter in there. And you're asking a really hard question because we don't know how to explain it. Right now, they are totally anomalous. And there are ideas, by the way, there's only 2 of them, and the 2 galaxies that we've discovered are quite small, they're dwarf galaxies. And one of the ideas is that these small galaxies have had interactions with bigger galaxies, and the big ones have stripped their dark matter from them. But that's only I'm like literally waving my hands. That's a very hand-wavy explanation right now, but we can't explain the galaxies without dark matter in them right yet. It's an open question. And we can't, that's the sort of thing you need Hubble and the big telescopes to address. And so we can teach the students about it, but we can't do anything directly with it here.
Gwen Ellen right
Yes,
here.
ma'am.
I think I'm not the first person to ask this question, but since Eugene, the distance between Eugene and Pine Mountain is a problem, in your new lab in Willamette Hall, will there be a space I could step into and be beamed up to Pine Mountain?
If you can help me discover that, that would be awesome. Because you know who drives the students to Pine Mountain every weekend? Me. I know Route 58 and Route 126 really well. Let me tell you. Yeah. Please help us build a transporter. So look, I'll tell you what. Let's do a couple more minutes, and we'll cut off just because I want to you all feel you're chained here. And then after that, we'll do one-offs or something like that. How's that sound?
Okay, I guess I have the next question.
Oh, yes, ma'am.
Yeah, the folks who discovered the black hole, how you said that they got a whole bunch of airplanes and they took them to a location. How did they know where to point the telescopes to look for this? Because you don't just go out and point a telescope at the sky and somehow find things.
No, I love your question. I'm laughing because it's such a pure question. It's a beautiful question. You're right. You can't just go to one of these telescopes and think, oh, get over there. No, my gosh, no. It's all super prescribed. You know where you're going to look beforehand. Now, this particular black hole picture is in a galaxy called M87. And we knew there was the black hole there beforehand. So we knew there was one down in there. And by the way, we knew because other telescopes have looked at this object and seen evidence for it. So the new thing is that this array of telescopes, by the way, all around the planet, they all work together, that allowed us to peer right down literally into the heart of the beast and image the thing for the first time. Before we knew it was there, but the black hole is, call it this big, and our cameras took pictures that had resolution this big. So it was just a big fuzzy spot. We knew it was buried down in there, but we couldn't get any detail on it until this new type of observation came around, and that allows us to peer right down into it itself. So we knew it was there beforehand. This is really, it wasn't a discovery image, it was the coming out party, so to speak, in some sense. It was the first picture that we could actually see of it, but we knew it was there beforehand.
One last question.
Yes,
Yes,
sir.
sir. You mentioned the supernova you took the picture of 55 million years ago.
Yes, sir.
How do you tell 50, why is it 56?
That's a great question because, let me go back here again. Sorry, blink your eyes real fast. Oh, I went the wrong way. Let's see, you're going to see this whole talk already. You've already seen it. So we happen to know, oh my God, I'm sorry, I misspoke. It's 35 million. Sorry, 35 million. But the reason we know that is other telescopes, not ours, bigger ones, have observed this galaxy. And there's a very interesting relationship called the Hubble law. And what that says is that every galaxy that's outside of our little neighborhood is moving away from us. And the ones that are farther away are moving faster. So you can make observations of a galaxy like this and measure how fast it's receding, by the way, which is called redshift. You measure the redshift, and Hubble can tell you how far away it is. So you measure how fast it is, and that tells you how far away it is. Turns out science is pretty cool.